Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of what it meant to say if a set was a subset of another set, and from this we built this idea or built this definition of the equality of sets. So we now know how to say whether or not two sets are equal. And continuing along this line, in this video we're going to continue to build some more structure on sets. And in particular, what we're going to do is we're going to look at ways of combining two sets together to construct new sets. And this will be done in two definitions that we'll look at, which is through something called the union of sets and the intersection of sets. So let's start with our first definition here, which is going to be that of the union of sets. So we start, as you might expect, with two sets, and we call those sets A and B. Then the union of A and B, we write in the following way. So we write it as this kind of AUB. Well, it's fairly obvious why we use this U, because we're meaning union. And what is the union? It's the set of elements X such that X is either in A or X is in B. So in other words, we take all the elements of A, we take all the elements of B, and we stick them all together, the kind of combination of all those elements, into a new set, and we call that the union. So you can otherwise think of this in kind of a Venn diagrammatic type of way, where you can say, well, if I take one circle as A and another kind of circle as B, and I kind of smush them together, this kind of big circle of them combined together is the union of A and B. So let's look at some examples of unions of sets. And as kind of before, we'll start off with some easier examples and then move to some harder ones. So the first one we've got here is let A be the set containing the element 1 and B be the set containing the element 2. What would the union of A and B be? Well, we just take all the elements of A, namely just 1, all the elements of B, namely 2, combine them together, and then construct our new set, which is the union. So the union, in other words, is the set containing the element 1 and the element 2. So that's our union. So another way of saying that is that the union is just the collection of all the elements of A and B. So we just take all the elements of A and all the elements of B, and we combine them together to construct this new set that we call the union of A and B. So what is our second example? In our second example, we're going to look at some of the number systems that we've looked at in previous videos. So we've got the union of the sets R and Q. So in other words, the real numbers and the rationals is simply just the real numbers. And in fact, this results from the fact that Q is a subset of R. And even more generally, so I kind of brought this up here, more generally, if you've got a set S and a set T, and S is a subset of T, then the union of S and T is always going to be T. It's going to be true for any sets. And that's effectively because this set T in this story is much bigger, right? It contains already all the elements of S are already in T. So I'm not gaining anything when I union them together. Effectively, all the information or all the data is just collected together in T. And the final example I want to consider is I want to take three sets here. So there's no reason why we can't union together as many sets as we want, right? If we know how to union two sets and that gives us a new set, then we can union that with another set and so on. So we can union infinitely many sets together, in fact. So what would the union of A, B, and C be here? Well, I take all the elements of A, all the elements of B, and all the elements of C, and I stick them together into a new set. But how I would write it is I write it in the following way. So I have here the union of A, B, and C. And actually notice it doesn't matter if I did A union B first and then C, or A then union B union C. And this actually is a result of the fact that the union is in fact an associative product. So that is to say that if you first do A union B and then C, that's the same as doing first B union C and then A. In fact, even more so, the union is also known as commutative, which is to say that A union B is equal to B union A. It doesn't matter which order you do it in. But looking back at this specific example here, we notice that even though some of the elements are common in some of the sets, for example, take the element 1, well, 1 is in both A and B, but we don't write 1 twice, right, when we take the union. And the reason for that is exactly what we kind of discussed in the previous video, where we noticed that there was an equality between two sets. Recall that we had this set that contained the element 0 and the element 1, and we had another set that contained multiple elements of 0, multiple 1s. And in fact, those two things were equal. So there's no need to actually repeat the elements over and over again. When I take the union of many things, even if those elements are common in many of those sets, I don't repeat them when I write them out because I don't need to, because that would be equal to another set with all those repeated elements. So I don't need to do that in this case. So I've just put a comment here to say, notice that none of the repeated elements are written within the union. We don't need to write them over and over again. So now that moves to our next definition, which is another way of combining together sets, which we call the intersection. And again, like before, we start with two sets. We're going to call them A and B. So let A and B be sets. Then what do we say? The intersection of A and B is defined in the following way, and we define it with this kind of upside down version of the union, kind of like an N. So how do we read that? That's the set of elements X such that X is in A and X is in B. So they have to be in both, So we're not taking kind of the elements in both and smushing them together and creating a new set. We have to check if it's in A, then it's also in B. We're kind of looking at the overlap of the two sets. And whatever the overlap is, we're constructing this new set that we call the intersection. And we also have kind of a sub-definition as part of the intersection. So whenever the intersection of A and B is the empty set, that is that there is no overlap, we say they're disjoint, which makes sense. If there's no overlap between the sets, then it makes sense to define them as disjoint. So let's look at some examples again, and starting off with some easy ones at the beginning. So we have here that we've been given A is the set 1, 2, 3. So that's the set containing the elements 1, 2, and 3. And B is the set containing the elements 3 and 1. What would be the intersection of A and B? Well, what are the elements that are common to both A and B? Well, both 1 and 3 are common to both of them. So that is that the intersection is just going to be the set containing 1 and 3. So another way of saying that is that the only common elements in both sets are 1 and 3. In other words, so unlike the union, where I combine together all the elements, the intersection only just looks at the overlap of the two sets. So let's look at another one. So much like before, or in fact, exactly like before, instead of taking the union, let's take the intersection of the sets, the real numbers and the rational numbers. Well, in this case, it's going to be the rational numbers. And again, this captures a more general property, but now it's the other way around. So if I have two sets, S and T, and if S is a subset of T, then the intersection of S and T is now S. And that's because if S lies inside T, then clearly the intersection, the overlap of those two things, must just be the entire set S. So this is different to the union, where the union had the property where the union of S and T was the whole set T. And the final example, much like before, we'll consider three sets. Similar to before, the union, we could take a union of infinitely many sets. We could also take the intersection of infinitely many sets. So let's just do it now for three. So here we've been given the set A, which is the elements containing 1, 8, and 3. B containing 1, 2, 7, 8, and 5. And C, 1, 3, 5, and 8. So we go through all of them, which elements are common to all three sets. So we write it out as A with this N intersect B intersect C, and we see that the only elements that are common in all three are in fact 1 and 8. And there's an important feature here as well that you notice that whilst A and B might have a kind of overlap between them, for example, A and B have overlaps of 1 and 8. That is exactly the same as A, B, and C. But let's look at the overlap between, say, A and C. Well, if I look at the intersection of A and C, that would be 1, 8, and 3. So I actually see that the intersection of A and C is slightly larger than the intersection of A, B, and C. But that might be to be expected because I'm looking at a kind of more and more overlaps and more sets, then that set size should be shrinking more and more because I have more and more conditions that I'm effectively checking. So I've just put a comment here to say, notice that whilst there is overlap between the pairs of the three sets, there is a smaller overlap between all three of the sets, which is what we're considering here because we're taking the intersection of all three. And actually, much like before, I should also comment that the intersection is also a commutative property. It has a commutative property. In other words, A intersect B is the same as B intersect A. And it also satisfies this associative property. That is, if you first do A intersect B and then intersect it with C, that's the same as doing B intersects C first and then intersecting it with A. So that's a feature of both the intersection and the union that you might not actually find in some other types of algebraic properties that we'll be studying further in the course. So that's where we're going to be finishing now. And continuing along this line, we'll kind of finish off in the next video our kind of final thing on set theory. We'll talk about the Cartesian product of sets. So this is another way of combining together two sets, but now to construct sets that actually have an order to them. So we're not just looking at unordered things. And in the final video, we'll move on to kind of discussing some mathematical proofs using the kind of notation that we've built up now in set theory and some of the logic that we've done in the earlier weeks. So again, I remind you to look at the notes on the Moodle page and also to attempt any questions within the module handbook tied to these questions we've discussed here. So thanks again for watching and see you in the next video.